Hello everyone, welcome to M3 lecture series Engineering Mathematics 3, which is from second year second semester subject. So within that already I explained some of the videos in our channel based on the linear differential equation. So that I already explained here in our channel how to find complementary function for our linear differential equation using synthetic division also, and nth order linear differential equation. I explained everything into my previous in my channel. Okay, so if you are interested to see this video, go and check in my playlist. So in my today's video we are going to start a very fresh new topic, which is a particular integral. Okay, so actually we know that the solution of a differential equation, how can we write the solution of a differential equation? Let me see here first. Solution, okay, solution or general solution of differential equation. Okay, linear differential equation. Solution or general solution of a linear differential equation can be written as complementary function plus particular integral. Okay, CF plus PI. So particular integral we write it is in the short form PI. Okay, this one is a particular integral. So general solution we write it as the solution for general solution of linear differential equation we write is the complementary function plus particular integral. Now about complementary function I explained everything in my previous lecture, okay, along with some of the example. So if you want to see this one, then go and check in my playlist. Okay, so in my today's lecture I'm going to explain particular integral. How can we work for particular integral? Okay, so let's get dive into a particular integral. Okay, so here we have some of the 3 to 4 standard results that are useful for finding the particular integral. So always it is quite difficult to use the these results. So at the end we go for using some of the tricks that to solve our linear differential equation for particular integral. And whenever we add complementary function plus particular integral, we get the complete general solution for our linear differential equation. Okay, yes. So let's get dive into our today's part that I will explain to you all. How can we derive? What is the logic behind of these results? Okay, I will explain here. Okay, so we are working f of d into y, which is equal to phi of x, which is a linear differential equation that I explained in my past previous lecture. Okay, so what is the type of linear differential equation we converted? F of d into y, which is equal to phi of x. Okay, this one is our linear differential equation that I converted into the polynomial of the form f of d. Okay, yes. So we write it's a particular integral. Okay, we write its particular integral, its pi, we write its pi as 1 upon f of d. Okay, we write it as the 1 upon f of d into phi of x. Okay, 1 upon f of d into phi of x. Now see that 1 upon f of d, it is the inverse operator for f of d. Okay, so we need to remember 2 to 3 points here. Okay, so if f of d is a simple operator, then 1 upon f of d, which is we write it as the inverse operator. Okay, let me write first point here. Okay, if f of d is simple operator, then 1 upon f of d is inverse. Then 1 upon f of d is the inverse operator. Okay, that need to remember here. So my next point it is here particular integral. What is actually the meaning of particular integral? Whenever we have constant term which is absent, in our differential equation, then we consider it as the particular integral. Okay, that means one more important point you all need to remember: constant term not present in particular integral. Okay, like a c1, c2, c3, these type of the constant terms are not present in our solution. Okay, then we write it as the particular integral. Okay, yes. Now let's derive the particular integral for our linear differential equation. So what we have here, differential equation into the form of f of d into y. Okay, Yes, so let's consider one of the auxiliary equation here. Okay, so you can consider anything you want, but for your better understanding and simple calculation, I will consider here f of d as a d minus a, f of d as a d minus a. Okay, as a simple operator or simple auxiliary equation. Instead of that, you can take anything, square, cube, or any power number, power auxiliary equation. It is up to you, but for your better understanding, I consider here d minus a. So while examples are coming, so we are going to consider higher powered or differential equation. Okay, so I consider here f of d as a d minus a, okay, as our auxiliary equation. So replace this auxiliary equation into our given polynomial equation, like f of d into y, which is equal to 5x. This one is auxiliary equation into y, which is equal to 5x. This one I consider as a nth order linear differential equation. Okay, I explained this one in my first lecture. Okay, replace this one. So f of d into y, which is equal to phi of x. Okay, so replace f of d as a d minus a. So d minus a into y, which is equal to phi of x. Okay, find out the value for y. So we are waiting for some values for x and y. So y of x can be written as 1 upon d minus a into phi of x. So y of x can be written as 1 upon d minus a into phi of x. Now we can see that d minus x I consider here as a f of d. So this one is the particular integral. I explained here how that particular integral it is coming. Okay, so what I have done, that f of d, okay, that numerator f of d, this one is the I consider at the initial particular integral. Okay, so how actually this is coming using this form. Okay, yes, I hope you all have understood why I have written this one as a particular integral. This one is the solution for y of x, which is our particular integral. Okay, yes, now we have to derive these three standard results. They are very much important for your examples, so be careful about them. Get focus here and let's get start our today's important result. Okay, yes, so let's start here with the our differential equation, f of d into y, which is equal to phi of x. Okay, f of d into y, which is equal to phi of x. We write we consider f of d as a d minus a. Okay, d minus a. So f of d as a d minus a into y, keep as it is this y, which is equal to phi of x. So I replace f of d as a d minus a. Now we are going to derive here the standard form of particular integral. Okay, yes. So now see that d minus a into y, which is equal to phi of x. I'm going to write y under bracket here. So I want to elaborate here as the differential term. So dy minus ay, which is equal to phi of x. So what I have done, I taken y inside that bracket. Okay, and as we know that capital D can be written as d by dx. Okay, capital D can be written as d by dx. So replace this value here. So I'm going to write this one as d by dx of y. Okay, d by dx of y minus a times y, which is equal to phi of x. Okay, so what I have done, I replace capital D as a d by dx. Okay, capital D as a d by dx. So d by dx into y minus ay, which is equal to phi of x. Okay, this one is our linear differential equation. Okay, now as we can see here, dy by dx minus ay. So this one is a first order, first degree differential equation. Okay, this one is a first order, first degree linear differential equation. How can we say that first order, first degree? So differentiation, it is only single times. That means first order. And the highest power of that differentiation, it is also 1. That means first degree. Okay, so this one is first order, first degree differential equation. This one is first order, first degree differential equation, and you all have learned how can we solve first order, first degree differential equation in your previous class or in your 12th standard, or you can check in my first lecture. I explained there how to solve first order, first degree differential equation. Okay, yes, mostly we use for solving their solution as a integrating factor and then the solution. Okay, yes, so whenever we have dy by dx minus, let me explain general form for this. So general form of first order, first degree differential equation is a dy by dx minus dy by dx plus py, which is equal to q. Okay, This one is a first order first degree differential equation. We write its integrating factor IF. Integrating factor is e to the power integration of p of x px dx. Okay, yeah, this one is integrating factor, and we write its solution as y of x into integrating factor, which is equal to integration of q of x into integrating factor dx plus c. Okay, so this one is a complete solution for our first order first degree differential equation. Okay, this is the method that we use for solving first order first degree differential equation. Now observe here, this first order first degree differential equation and this one is both are looking quite similar. Okay, so use this method for solving this solution. Okay, so let's get started start this solution. Okay, so see that I'm going to solve this one using this method. Okay, dy by dx. Now observe that plus py, which is equal to q, the value for p we write as a value for p here, we write value for p as a minus a. Okay, so compare this one py with a minus a, so we write p as a minus a, and q of x, this one is actually q of x. Q of x is equal to phi of x, so we write q is a phi of x. Okay, so I got the value for p as minus a, q as a phi of x, with comparing both of these linear differential equation, okay, of first order first degree. Okay, now let's go for finding the integrating factor. So I want the integrating factor here. Okay, so integrating factor can be written as e to the power integration of p of x dx. Okay, so e to the power integration of value for p, which is a minus a dx. Okay, so minus a, it is a constant, take it out here, so we write e to the power minus a into dx. Okay, so we write e to the power minus a, integration of a dx, it is opposite of a differentiation, so we write minus ax. Okay, yes, there is to minus ax. This one is our integrating factor. So I have to replace that integrating factor into that solution, y of x into integrating factor, and q of x replace that phi of x. Okay, so what we write here, a solution y of x into integrating factor. Integrating factor is a minus x. I'm going to write integrating factor directly here. Okay, yes, e raised to minus ax, which is equal to integration of a q of x. What is the value for q of x, which is a phi of x we have here. Okay, integrate q of x is here phi of x. Okay, so I consider with the given linear differential equation. Okay, so using this comparison, I got the q of x as a phi of x. Okay, which multiplied by integrating factor. What is the value for integrating factor? E to the power minus ax. Okay, integrating factor is e to the power minus ax. Okay, and after that dx plus c. Okay, this one is our required solution for our nth order first order first degree differential equation. Okay, so we want the solution in the form of y of x. So now see that e raised to minus ax is here as the negative power, so if it goes to the other side, obviously it goes to the positive power. So we write y of x, which is equal to e raised to positive power ax phi of x e raised to minus ax dx plus c. E raised to minus x, it goes to the e raised to power ax. Okay, how I have written? Now let me explain how I have written this step. E raised to power minus x, it is here. So when it is multiplicand here, when we take it to the other side, it goes to the denominator, and of it obviously if it is denominator for this term and this term also. So if a denominator has negative power, when we take it, it goes to the positive. When we take it our numerator, it goes to the positive. Okay. And one more note you need to remember, at the initially I explained here when it was the starting of our lecture, I explained here constant term not present in our particular integral. So this term, it will be vanishes, okay, from our solution. So what is our required solution? We write here y of x, which is equal to e raised to power x integration of phi of x into e raised to power minus x dx. Okay, this one is our required solution, okay, which is a y of x. Now see that we are working on a particular integral. So particular integral, that means we have to solve the auxiliary equation here. Okay, so for auxiliary equation, replace the value for y of x. Okay, so here's from that y of x is going to come. Now see that at the starting I explained here the value for y of x. Okay, so value for y of x, it is here. See that value for y of x where we found here. Yeah, this one is the value for y of x. Okay, so y of x is equal to 1 upon d minus a into phi of x. Replace this value here, y of x. Okay, so we write 1 upon d minus a into phi of x, okay, as a y of x, okay, which is equal to power e raised to x integration of phi of x e raised to minus ax dx. Okay, this one is our required first result, which is important, very important, going to in our next lecture. Okay, so in our next example, this one is a very important result for our next lecture. Okay, next lecture means for finding the particular integral. Okay, this one is 1 upon d minus a into phi of x, which is e raised to x into integration of phi of x e raised to minus x dx. Okay, as it is a particular integral, so we don't have constant here. So we have written as a d minus a, but it is possible that 1 upon d plus a, it is also the auxiliary equation. Okay, maybe a, it is also 0. So take these terms. Okay, take a as a 0, a as a positive, and then find out the particular integral. This one is our first result. Okay, so using this one, I'm going to solve next one here. Okay, be careful here with another result. So I'm going to solve this one here in this bracket. See here. So replace a as a 0, put a which is equal to 0 in this equation. Okay, so if I'm going to replace a as a 0, then we write this term as 0, this e to the power 0 is 1, e to the power 0 which is 1. Okay, so we write 1 upon d, okay, minus a becomes 0 into phi of x, 1 upon d into phi of x e raised to x, which goes to the 1. We are not going to write this one, so phi of x, write this one as it is here, e raised to minus x, that means e raised to minus of 0x, which is also 1 dx. Okay, this one is also second result, which is very much important for our particular integral. Okay, so need to be careful with this result. And last one, replace minus a by plus a. Okay, so replace a by minus a. Okay, replace, if a as a minus a, that means minus minus goes to be the positive, so we write 1 upon d plus a into phi of x. We write this one as 1 upon d plus a into phi of x. Replace a by minus a, then that means e raised to minus x, a as a minus x, integration of phi of x. Okay, replace a by minus a, we write e raised to minus of minus ax, that means e raised to positive ax and dx. Okay, this one is also third result. These are very much important. Okay, I hope you all have understood these three results. Okay, this one is a second, this one is third, and this one is our first result. Okay, these three results are very much important, that we are going to use these results for finding the particular integral. Okay, now see that if you want to see the entire solution, you can go through this one, my notes. Okay, you can see here particular integral. Okay, so if you want my notes, you can refer my notebook also. Okay, I'm showing you all here notebook also. Okay, see that here in my notebook I written these notes, see, for particular integral. Okay, you can refer my notebook here for particular integral. Let me show it here. Okay, so this one is my notebook, that you can refer this solution for your reference. Okay, so this is entire solution. Okay, and what are the important results that I explained here? These first three results are very much important. Okay, take note as these three important results and keep it for your preparation. I hope you all have understood my today's lecture. So this one is completely based on the particular integral. So in my next lecture, I'm going to explain to you all some of the example based on the particular integral and the process, that how can we find solve the linear differential equation. So if you want, these are the three steps only, you can refer it here. So I have written here method for solving linear differential equation. First of all, we convert it as the auxiliary equation. Okay, so I already explained how to convert auxiliary equation by using our differential equation, linear differential equation. Then further we go for finding complementary function. Okay, already you know these things, I explained in my previous lecture. For finding particular integral, I will explain to you all in my next lecture. I explained method, how can we find, how can we deal particular integral for a linear differential equation. I already explained in my today's lecture. So only the some examples still it is remaining. I will take it to the my next lecture. Okay, and then at the end we go for total solution, complete solution or general solution as a complementary function plus particular integral. Okay, so that is the method that we use for use to find out the solution for our linear differential equation. Okay, so that is for our today's lecture. I hope you all have understood my today's lecture. and go for revising the notes using my video lectures. So if you want anything more, or if you have anything doubt, difficulty, let me know in my comment section. I will come up with a similar video. So thank you everyone. Thank you for my today's lecture.